Hi everyone. So in today's webinar, the topic we are going to discuss is blockchain sharding, commonly known as a good approach to enhance blockchain scalability, throughput, and accessibility. The speaker will be Ziwei Wang from Wuhan University and Cong Wu from the University of Hong Kong. They will first introduce a survey of existing sharding approach, and then most importantly, discuss potential sharding designs in Hedera. So without further ado, let's start. Okay, this way you can go ahead to present.
Okay. Hi, everyone. Welcome to my presentation. My name is Ziwei Wang, and I'm currently pursuing a master's degree in electronic information at Wuhan University. My research focuses on vulnerability mining in blockchain smart contracts. Today, I will be talking about the current research on blockchain sharding technology, including its mass applications as well as its potential in Hedera. Sharding was initially proposed for traditional distributed database and is a well-researched scalability technique. In blockchain, sharding is also used to improve scalability. The basic idea is to divide the network into many small committees, each with a reasonably small constant number of members. I opened the video. Sorry, I forget it. Okay, let's go back to PowerPoint. Then transactions are split into non-overlapping subsets, and each committee is assigned a subset to process. This way, the communication complexity within each committee remains as the number of committees increases linearly with the number of networks computing power. The transaction throughput in the network also grows linearly with the network's computing power. This diagram shows how a typical sharding scheme works. On the right, the blue chain represents the transaction set of shard 1, while the blue circle on the left represents those responsible for processing the transaction in shard 1. It can be categorized into 3 types based on the object being divided. The first type is network sharding. While the nodes in the network are divided into different committees, the second type is transaction sharding, where transactions are divided into assigned to different committees. Third is sharding, where the ledger is split into different parts and each committee only needs to store the portion of the ledger related to its shard. As shown in the diagram in the lower left corner, these 3 types of sharding apply at different layers of the blockchain. In a sharding model, it is common to combine several types of sharding. In the Venn diagram on the right, a model that uses 2 types of sharding is called partial sharding. One that uses all 3 types is called flooding. Elastico is a classic blockchain sharding solution designed for synchronous network models and blockchains that use unspent transaction output-based account model. It is a partial sharding approach using both network sharding and transaction sharding. Like Bitcoin, Elastico blockchains in Epoch divides transactions into different subsets based on committee IDs and assigns them to the corresponding committees. Within each committee, members reach consensus on their assigned transaction set or shard using the practical Byzantine fault tolerance protocol. Finally, a Philo committee is responsible for combining these shards and broadcasting the results. This committee also generates for the next epoch. In terms of security, Elastico can tolerate up to 1/4 of the total nodes being Byzantine adversaries from a performance perspective, the communication complexity of the entire network is close to ON, while the bandwidth requirement of each node is constant. Transaction throughput is linearly with the network size. Another academic sharding solution is rapid chain, which is a full sharding approach. Its committee division design is similar to elastical, but it introduces some key differences. Rapid chain adds more randomness and a committee reconfiguration mechanism epochs to enhance security. Additionally, it takes into account the dependencies between actions and the designs specialize the routing and the communication methods for committees to validate coarse shard transactions. Rapid chain uses a Byzantine consensus algorithm based on a synchronous protocol, which increases the tolerance for Byzantine nodes to up to 1/3 of the total nodes in the network. Since then, many new sharding solutions have been proposed, each designed to suit different network environments and account models. Here, I have provided a simple comparison of 4 such solutions. Due to differences in the performance of loads used in the experiments of these papers, the throughput and the performance in the table may not fully represent the relative performance of each solution. However, all of these solutions are designed to enable transaction throughput to scale nearly with the network size. In terms of sharding applications, several blockchains in the industry have already implemented sharding technology to improve scalability and reduce transaction fees. Ethereum stack sharding divides the network into 64 new chains, as known as shards. Similar to discussed earlier, each node only stores a subset of the transaction data. Ethereum also uses roll-up technology, which allows transactions to be bounded off-chain, generating a cryptographic proof and then submitting it to the chain. This way, Ethereum can process transactions and smart contracts through data sharding alone. Finally, Ethereum uses a block proposal to create blocks for all the shards, helping to lower transaction costs. Polkadot uses a unique approach to sharding. With its relay chain and parachain structure, transactions on the relay chain refers blocks from the parachains, and the parachains themselves are the shards for transactions. Within each parachain, collectors sub-blocks, while validators write these blocks and add them to the shard. This design allows for parallel processing for transactions across different parachains. Finally, there is the Zilliqa X-shard solution. What makes it different is that the nodes in the network can belong to multiple shards at the same time and process transactions from different shards concurrently. This allows the network to scale its throughput dynamically depending on the needs of the application built on its infrastructures. Could sharding be applied to Hedera? What benefits could it bring to Hedera? Let me first introduce Hedera's design and its Hashgraph protocol. In Hedera, nodes communicate using the gossip about the gossip protocol. Each time 2 nodes communicate, it gossip sync, where they share all the events they know. In Hedera, an event is like a block in a traditional blockchain. It contains a signature of the creator node and a time step, a set of transactions, and 2 hashes. One is the hash of the previous event created by the node itself, and the other is the hash of the previous event created by the communicating node. during gossip sync, nodes trace back through the event hashes to check if they already have the ancestor events, ensuring consistency in the hash graph. After receiving a gossip sync, nodes create a new event and initiate another gossip sync to another node. In this way, events are linked through the hashes of the previous events from both the communicating node, forming a cyclic graph, which is the hash graph. Members of the network use the hash graph to perform a virtual voting process to decide the order of transactions. Since every member has a complete copy of the hash graph, they can locally calculate the voting results of other members without any further communication. This design gives the protocol excellent scalability, very low latency. Even so, sharding could further help Hedera reduce storage requirements, cut down on communication overhead, and enhance security and reliability. Since each node stores the entire network's hash graph, the network grows, the memory demand increases significantly. Additionally, during the gossip sync process, transmitting the entire graph has substantial communication overhead, and this overhead grows as the network size expands. Finally, sharding can improve Hedera's security by making it harder for adversaries to launch successful attacks. By storing redundant data across shards, sharding increases data availability and enhances the overall reliability of the network. The solution is designed with the following approaches to achieve the goal mentioned earlier. First, by dividing the network loads into multiple small local committees, we can reduce the size of hash graphs stored by each committee member. This also minimizes the communication volume and the frequency between committee members. Additionally, randomly assigning committee helps enhance security, making it harder for adversaries to execute attacks like cyber attacks. Second, a global committee is set up to handle routing and propagating cross-shard transactions. This global committee is also responsible for maintaining backup copies of the hash graph from the local committees, ensuring better data redundancy. Finally, committee will be able to figure to prevent from being overtaken by adversaries and to mitigate the impact of fault nodes. Next, I will explain more of the design details. This diagram provides an overview of the design, including the setup of the local committees and the global committee, as well as how intra-shard transactions and the cross-shard transactions are handled. In the diagram, the orange nodes represent local committee A, and the green nodes represent the global committee. Both the local committees and the global committees run the hash graph protocol. The local committees only store the hash graph for their own shard, which reduces the storage and the communication requirements for the nodes. The global committee, on the other hand, not only stores its own hash graph, but also keeps the hash graphs from the local committees. This enables the global committee to assist with cross-shard transactions and improves data redundancy across the network. Network nodes are randomly assigned to different local committees. And within local committee, one member is randomly selected to be a coordinator. All the coordinators from different local committees form the global committee. Therefore, the coordinators are are members of both a specific local committee and the global committee. The coordinators store both the Hashgraph of their local committee and the Hashgraph of the global committee. This setup ensures that intra-shard in transactions can be processed within the Hashgraph protocol to maintain consistency and agree on the order of transactions within each shard. Cross-shard transactions will be a bit more complex. For example, local committee A will include related to cross-shard transactions with local committee B. These events will be sent to coordinator of the local committee A through gossip sync. The coordinator then adds these cross transactions to a query and creates a new event that does not contain the cross-shard transactions. The coordinator will then gossip sync event with the other members with the local committee A. Since nodes in each committee don't have the Hashgraph from other shards, they cannot accept the event from other shards directly. Therefore, the coordinator cannot immediately gossip sync the created event with members of the global committee, as they will not event due to the lack of Hashgraph of committee A. After the other members of the global committee perform gossip sync with the coordinator of local committee A, the coordinator will create an event that includes the cross-shard transactions and then gossip sync the event with the global committee. One coordinator of local committee B learns about these cross-shard transactions. He will also add them to their catch query. At this point, the coordinator can create an event and perform gossip sync with other members of the global committee. Just as the coordinator of local committee A did. Finally, of local committee B initiate gossip sync with the coordinator of local committee B. The coordinator can create an event that includes the cross-shard transactions from the catch query. The coordinator will then perform gossip sync with the other members of local committee B. In this way, the cross-shard transactions are known and accepted by the target committee. The local committee will synchronize and store the hash of other shards through the global committee. This setup allows for easy committee reconfiguration at regular intervals, ensuring flexibility and security in adapting to changes in the network. Committees will randomly reorganize depending on the Hashgraph they store. Nodes can switch the Hashgraph to communicate and gradually consistent by gossip sync with new committee members. To conclude, Sharding represents a powerful solution for improving scalability, reducing communication overhead, and enhancing the security and reliability of blockchain networks. By applying this approach to Hedera, we can significantly optimize data storage and transaction processing, while ensuring a more robust network. With the introduction of local committees, coordinators, and the global committee, Hedera can efficiently handle cross-shard transactions, improve redundancy, and adapt to changes in a secure and seamless way. This paves the path for a more scalability and resilient future for Hedera and its economic system. Thanks for your attention. And my speech is over. Thank you.
Okay, thanks, Ziwei, for the interesting presentation.